So the big question we set out to answer is what can we learn about art from mathematics? And specifically, what can we tell two paintings apart? And we decided to focus on the texture of the artwork. So imagine the visual texture between an oil painting versus a tempera versus a watercolor, as opposed to something like brushstroke or the colors of the painting itself. So we worked off a paper called Data Representation using the Weil transform. This paper worked on taking little patches of fabric like denim and cotton and wool and seeing if they could visually tell them apart using some big fancy matrices. Okay, so our process starts by taking an image. Here we have Van Gogh's oil painting called At the Foot of the Mountains, and we throw it through MATLAB and turn it into grayscale. We take little square patches like this, are little grays and blacks and whites, several hundred times, and we pull them out.
There you go.
So these little patches can be represented by numbers from 0 to 225. Black is 0, white is 225, and shades of gray are in between. We take those and we pop off the subsequent columns and make it into a column of patches and a column vector. We call this little y. The cool thing we can do with this is when we take y transpose, so a column vector versus a row vector, we get a really nice symmetric matrix. So here, match, here, and here. This is some of the 0. So what we're going to do with this is we're going to take this matrix and represent it through a basis of other symmetric matrices. We're going to take those coefficients and we're going to talk about them. So we have a symmetric matrix, and we have, in theory, another one from another piece of art we're comparing, and we're going to represent them through a basis. And our special coefficients for this basis are the Weil coefficients. So before we get into that, I'm going to work through a couple of things here. Our work relies on these two matrices. They both square to the identity, and they're anti-commutative. And what we're going to do with these is a special operation called the Kronecker product, which is defined as such, and I think it's best illustrated with an example. So given these two little matrices, the Kronecker product of A and B, we pop all the entries out of A and multiply each entry across B and kind of pop our submatrix C brackets off, and we get this nice 4 by 4. These grow really, really fast, so we have to make MATLAB do some of the work for us. Another thing we need to know about is we have two vectors, A and B. They're binary M tuples, so they have entries of 0 to 1. So a little example to illustrate the point. M is 4, we have A is 1, 0, 1, 1, and B is 0, 1, 1, 0. So now we have the Heisenberg-Weil group of order 2m. So we get to pick our m, and we represent elements of our basis with the DAB. And so working kind of from the middle, when we have an A vector like the one on the previous screen, every one of these is x raised to that power 0, 1 from a couple of screens ago, Kroneckered across x raised to the next one. And the tricky part we have with this is when we write our A's, they're written in order 0, 1, 2, 3, up to n minus 1. And when we compute these, we actually have to reverse the order. So we had a little trouble getting the hang of that at first. So the same thing works for D0B, and then we take those two things and multiply them together in the typical fashion. So, small example, if we want to calculate D01, 1, 0, first we calculate the two components, D01 with the 0 vector, and D0 vector 1, 0. So D01 uses the parts of our x against the identity. That's the 1 and then the 0. So x has entries on the op-ag of 1, multiply through each instance coefficients of the 2x2 identity, we get this guy. For our D0B, we have the identity chronicled against our Z matrix. So we have 1s on the diagonal multiplied against our little Z matrices, which gives us this guy. And then we multiply those two together, and we end up with this nice symmetric matrix, which is one of the elements of our basis. So now we're going to define our basis, which is an orthonormal basis, as 1 over 2 m to the lambda over 2 times all these DABs, where D transpose, or A transpose B is 0. These are all the elements of the Heisenberg Weyl group that square to the identity and are symmetric. The ones that where A transpose B is 1 are not symmetric. So then, to get the coefficients of our bases, we take, for any given A and B vector, we can compute this using this little definition here. Note that each coefficient relies on the particular element of our bases that we're trying to find the coefficient for. And then we can represent any symmetric matrix as the sum across all those different AB vectors where the transpose is 0. So this is an example. We have 16 matrices. So you can see some of the symmetric ones, like this row, number 5 there, number 7 there, and things like 8 and 6 are not symmetric, so we end up excluding them when we start to calculate things. And the question I love answered when I am sitting in the audience is, why do we care? So this is from the paper we worked off of. You can kind of see where we have genes of cotton and a couple of example patches. Their size was 2 to the 4, so 16 by 16. And you can see this is a graph of all the coefficients. So when you have a 16 by 16 tiny patch, you get 136 different DABs. So that makes it really hard to compare, like, how similar are those two? I can't tell by looking at it. So what we do is we take principal component analysis, and we shrink it down to 3 dimensions, and we kind of cluster and graph them and see if all the coefficients from painting A kind of group together and against painting B. So this is one of our experiments. Here you can see Van Gogh's Apricot Trees and Blossom. It's an oil. And here we have Pink Peach Trees, another watercolor by Van Gogh. This was kind of one of my control experiments. I kept, same painter. They're about a year apart. Tree is the big subject. Not much of an art guy, so I screw some up. But the coefficients from the oil cluster pretty well. You can see here in the yellow, a little difference, and then all the watercolor coefficients end up here in purple. So we can make a case that we're telling them apart using math. So here we have the same oil, and we have Duccio's Madonna and Child, which is a tempera. So I found this an interesting comparison because I'm sure we've all mostly seen oil paint, so there's a distinct texture there. But an old tempera like this would have been painted on a wooden board that was primed, and then the layers of the tempera paint, which are very translucent, one by one, have to be built up over it to get the depth of color. So we should get 2 really distinct textures, and we get a pretty good case for that here based on our oil coefficients. So we found that those 2 were pretty good, but not all of our painting pairings worked out so nicely. We had one particular set that was another Van Gogh oil versus Van Gogh watercolor, where it really just kind of wobbed together. We kind of started asking our questions: does brushstroke play into this? Subject matter, because they were very similar subject matter as well. So looking forward, we kind of want to start taking bits of, like sub-bits of paintings. Like we're going to compare, the skyblocks from 3 or 4 different artists in different mediums and see if maybe we can kind of cut down some of the variables of different subject matter, something like that. So that's my talk.